Oh, don't make me say it. Don't make me say
All
it.
right, so you always have potential energy,
That's my job.
but sometimes you have potential and kinetic.
Okay, that's where I was confused.
Okay, you always have potential, sometimes you have potential and kinetic. When do you have potential and kinetic? When the temperature is doing what?
Increasing.
Increasing. And when is the temperature increasing? When there's one state or two states?
One state.
One state.
So on the ups.
On the ups,
Up, so up. So 1,
That
3,
will be-
and 5.
potential and kinetic, potential and kinetic, and potential and kinetic. Now, when you're at the flat, when you're at the level where there's no slope, what's happening? You're still adding energy because look, the minutes, time is marching on. It's still on a heating plate, or it's still being heated by something. Energy is going into that. Right here, what states do we have right here at 2 on page 577?
Solid liquid.
We have solid and liquid. Okay. Energy is being poured into that system. And energy can't be,
It
just
only has one job,
lost or anything. What is the job it has?
to increase its temperature.
But it's flat, so it's not.
Change of state.
So what's true about the particles in a solid?
They're very close together.
They're close together, and what about the strength of attraction?
Very high.
They're strong. So all the energy at this point is not warming it up. It's going to do what to the ice?
Trying to melt it.
Trying to melt it,
Break up the
trying to
particles.
break up the bonds, those bonds that are holding it in that vibration structure. Okay. The energy is not increasing the temperature, it's breaking those bonds that are holding it in that solid state. Now, once all the bonds are broken, then what happens?
Temperature is able to
Then
increase.
the temperature, so now you have all what? By the time 3 starts, you have all what in there?
Liquid.
All liquid. So if you have ice in your drink, it's not like your drink is getting colder and colder. The energy, so your drink is like staying at the same until all that ice is melted, and then it's going to start decreasing. So when there's 2 states in there, all the energy is going to breaking those bonds. So in number 4, what's all the energy going to?
Separating the bonds of the particles. So the particles are able to move further apart away from each other and lose their attraction.
So potential energy, you can say?
All going to potential in any of those flat ones. And when will it start going?
Potential and a kinetic?
And then
Always potential.
When all the particles holding it in that liquid configuration, when all those strengths of attraction are now separated, then it will start to There's
increase.
a mistake on the y-axis. What is the mistake?
Oh,
It
it
goes
should be
from-
100. I
It
changed
should be 100 instead of 200. So it goes 80, 100, 120.
I changed it.
So you will need to know these things. Look at the point where water changes from a solid to a liquid. What temperature is that? 0. And at what temperature does it change from a liquid to a gas? 100. And until,
But that's for water.
and then from a gas, we just stop there.
4 is potential and kinetic, or it's only because it's just a straight line, it's only potential energy?
Only potential, because is the temperature changing?
No.
So the kinetic is only on the ups.
So it's not boiling at this point?
No. Not until you get
It's
Because
still
it's at
boiling.
100. Isn't the boiling point
It's
of
boiling. It's still bubbling,
bubbling. It's
Okay.
but the temperature is not going up.
it's
the
it's
temperature is the
constant
same.
It's
So it's
holding
still
its
just warming.
temperature.
Yeah, but if you need to see the
It's
bubbles,
not warming. It's not warming.
It's holding its
Bubbling
temperature.
at
It's
100.
easier to see when it's ice and water. When it's okay, so you've got some ice that's super cold, super cool, and once it hits 0, it's kind of like at that point, if you add a little bit of energy, it'll melt. If you take a little bit of energy away, it's going to freeze. So right at 0 is kind of, you know, that point where if you add a little energy, it'll melt. If you take a little away, it'll freeze. So we're at 0.
It would be slush.
Well, yeah.
It'd be about that slush because it could go either way.
So
depending on
as
what you
long
do.
as there's still ice and water, the temperature is not going to change.
So for number
Once all the ice is gone,
then the temperature.
now the temperature, you're still adding energy, now the temperature is going to start going up.
So for number 4, we put a liquid and gas, and then we, for the changing state, we would put like a boiling, not
Yes.
warming. Okay.
Now, look at line 2 and look at line 4. Does it require more energy to go from a solid to a liquid or to go from a liquid to a gas?
A liquid to a gas.
And why do you say liquid to a gas?
Because it took more time. The line is longer.
The line is longer. It's actually, if you count the squares, it's about 10 times more energy in this case. Now, I could draw on the exam a different substance where 2 would be really long and 4 would be really short. Okay? Then you would have to say that one takes more energy. So that line, the line that has no slope, the line that's just flat, that can indicate to you how much energy it takes to change that state. Now, the other changed, and Kelly said it a second ago, talked about the slope of 1, 3, and 5. Okay? Just looking at 1, 3, and 5, just eyeballing it, which one seems to have the highest slope?
3.
Warming liquid.
Which one has the most severe slope, the biggest change?
5.
So we have 3, we have 5.
5. The steepest slope, you mean?
The steepest slope.
Is that 5?
5. Look at 5. Now, the steepest slope means what about the rate of change?
It changes faster.
Quicker.
It changes faster. Okay? So 5 is changing faster. So does that mean that it requires less energy or more energy to change?
Less.
Less energy. Now, remember specific heat.
I
Okay?
made triangles.
Where did it mention specific heat?
I made triangles.
How hard people were.
Well,
Okay.
I made triangles.
So Kelly took and made triangles so she could kind of get a better idea of
And then you can count.
which one
Takes more energy. Does that make
has the
sense?
higher rate of change. That's excellent. Okay, which one has the higher rate of change? 5 has the higher rate of change. A higher rate of change, does that mean it takes more energy or less energy
Less.
to change? It takes less energy. Now, specific heat is the amount of energy it takes to take 1 gram of that substance and raise it 1 degree. Okay? The 1 gram of that substance and raise it 1 degree.
Specific. What page was that on?
We couldn't find the page.
I have so
Okay.
much junk all over my pages. I can't
So
remember.
that's what specific heat is. So does it take, it's the amount of energy needed to take 1 gram and raise it 1 degree. So if you look at 3 versus 5 on page 5-77, if you look at the slope of 3 versus the slope of 5, okay, which one requires more energy to change 1 gram? 3 requires more energy. The slope is not as steep. Okay, that's where some people get mixed up.
That's
So-
why it's requiring more energy.
The rate of change is slower because, say it, Fatima?
It's taking up, the slope is not that steep, it's taking up only 4 squares.
Mhm.
It's taking up 4 squares in comparison to just 1 square and 5 and 1. So,
So it requires more energy, therefore it has a higher specific heat. The more energy it takes to change 1 gram, 1 degree Celsius, the higher the specific heat. And what does that say about the slope? The rate of change is slower, so the slope is going to be less steep. So that's where people get it all mixed up. Remember, a steep slope means the rate of change is really fast. That means a low specific heat. It doesn't take much energy. But a more gradual slope means you have to add a lot of energy to change that. And what causes the change? What are you doing to the strength of attraction?
Trying to reduce it.
Okay, so it's really